So in our homework, it says here in item number 1, in problem 2, it says draw the moment diagram ignoring the self-weight of the beam. So please do not spend any time and don't try to figure out the self-weight of the beam, and don't do the moment like this. We are not going to do it this way. It's going to be only the moment diagram based on 2-point loads, 10 kips and 10 kips. It's going to be all the loads applied. Self-weight is ignored in this homework. This says here, determine the maximum moment. So what you'll do here, based on this moment diagram, you say here is the maximum moment. After you do this, it says here, check if this beam has cracked due to the given load. Now compare this applied moment from this maximum moment out of the diagram and compare it to the cracking moment. If this moment is lower than the cracking moment, it means that the beam did not crack yet. Be sure that you clarify your answers. When I look here at the answers, when we do grading, we look for 5 answers for problem number 1. If 2 answers is provide kind of the same answer, right? Like inherited within the problem itself or within the answer, I'm not going to consider this to be an answer because I may miss it. So be sure, for example, when it says determine the section moment of inertia I and then section modulus S, you put this in a box, the value, you put the value in a box and say, here's the moment of inertia, here's the section modulus. Make it easy for me to find out the answer in your solution. When it says here, draw the moment diagram, ignore the self-weight. You're going to be here drawing the moment diagram. This is going to be item number 1. Item number 2, determine the maximum moment. Don't just consider that by drawing the moment diagram and showing the values, now you determine here the maximum moment. You need to come here, you're going to say item number 2, maximum moment equals, and then you put the value. If you didn't do that, I'll consider that you don't know where the maximum moment is at, or what the value of the maximum moment. So be sure that in your answers, because I don't want you guys to lose points. And of course, this would apply to the project and applies to your midterms and your final exam. Be sure that you clarify the answer and maybe put in the box. And please try to work a little bit in your handwriting. If you guys are planning to do your handwriting and scan, I'm okay with this, but please work on your handwriting. Any questions on this homework before we move forward to today's lecture? You're good? No questions at all? All right, good thing about this homework that you have 2 examples and the slide set that shows you exactly how to do it. Right, perfect.
Professor, are you going to post that homework after class?
Yeah, it should be there now, but I don't know why it doesn't show up. But it should be there in minutes or maybe right after the class.
Okay, thank you, Professor.
All right, thank you. All right, now we're going to move here to slide set number 3. It is about reinforced concrete member design. Now, slide set number 2 was mainly about performance of unreinforced concrete, uncracked concrete. The purpose of the previous slide set is to study the performance of concrete before we're adding the reinforcing and before our applied moment is going beyond the cracking moment. Now we're going to start to look here at the real design of a reinforced concrete beam. So we're looking here at a reinforced concrete building, like a section through it. You are trying here to identify members that you are going to be working on their design. As you see here, we have the second floor, and then you have the first floor, and then you have this. It's going to be like the basement, if you like. In this basement, you have concrete slab that is just supported completely by the soil. This slab here, we call it slab on grade. It is completely supported by the soil. We're not going to be doing a design for a slab and grade in this course. But when you look here at the first floor, it says here supported slab. So you have a reinforced concrete slab supported by beams. And if you think here about this beam from the way it is drawn, this beam is continuous. It's coming from a column to a column. Very similar to this beam. From this column, it is running all the way across to this column. And then here we have some beams. If you look here at this beams, you should say, maybe I'm expecting a beam to be running across like this. These beams are supported by columns. And then at the end, this column is supported by a footing. Also, we have this wall. We call this a basement wall. It's going to be the common term that we use in our business. We call it basement wall, not foundation wall. Foundation wall is okay, but you may also call it a basement wall, which is more common. Another type of buildings, if you notice here, columns were rectangular in section. Here the columns are round. If you notice here, the big difference in the slab itself of the floor system, the floor framing, here you have something that you call joist, we have beams, right? But here we have no beams at all. It is true, you may have a building without any beams. In a case like this, you're going to have the slab support directly by columns. We call this flat plate or flat slab. The good thing about it that you can live with this exposed slab and you don't need to see any beams. So in certain applications, you're going to see something like this. The slab is directly supported in columns. What happens is this roof is supported by, let's say, these two columns and maybe another two columns here in the back. Load comes from the slab to the column of the second floor. And then again, the load of the first floor is going to be supported by the first floor columns. And this first floor column supports the load coming from this slab and from this column. But like here, just go for simple discussion, we're going to say, let's say I have here a point load coming from this flat plate, and let's say it's equal to 5 kips. What's the kip? 1,000 pounds. So 5 kips of this point load coming from the roof. And from this first floor only, I have a point load that's coming to this column section. Let's say it's going to be 8 kips. So now someone's going to say, how much is the force on this column of the second floor? I'm going to say the total force here is going to be equal to 5 kips. But how about the load that comes here to this column? And say the load that comes to this column here, which means it's going to be the total load of the two loads above, it's going to be equal to 5 plus 8 is going to be equal to, you can see here 5 plus 8 equal to 13 kips. Does it make sense? How about this footing? How much force does this footing support? You can say it's giving the total force like 13 kips. It's just some numbers, right? Just to explain the idea, but in an actual building, you're going to be doing detailed analysis. You'll figure out the exact amount of force coming from here and from this first floor. And if you have 10 floors, let's say, you're going to do each floor separate, just add them up at the bottom to determine the design force on the bottom column. Here's a section through a building. As you see here, we have concrete slab supported in a couple of beams running across. Then you have a column here that takes the load from the top, and then the second floor, if you like, goes all the way down, goes to the basement, and then at the end, you're going to see here a footing. Here's the foundation system. You have a few columns, and then you have basement walls, right? And then you have interior walls. Each one of these members, they support vertical loads coming from the levels above. At the end, they deliver the load to the foundation. And from this pad or this concrete footing, it goes to the soil. So in our design here, we need to be sure that we have a continuous and a strong load path components. The load path in this case would mean that you have the loading, and the load comes, let's say, from the slab to the column, slab to the column, to the footing, to the soil. So, all right. Here's some load here. You see this area here is loaded. Let's say here's a surface load, or maybe some line load, or maybe some point loads. All of these loads are supported by the slab directly. So what happened, the slab is going to be taking all of this load and distributed on this 4 beams on the perimeter. Now the beams are taking the loads and then drop it down or deliver it to the columns. You have here 4 columns. Column is going to be taking this load, delivered to the footing, and the footing at the end give it to the soil. So in our design here, if you're doing here a complete design of the building, first you need to be sure that the slab is strong enough to support the loads. So as the beams, columns, footings, and then at the end the soil. You need to be sure that this soil is able to support the given loads. This is what you call here design. Design means that you come up with the member section, which means size, width, and depth, and the amount of reinforcement that you put in there. So coming up with the dimensions of the structural members and the amount of reinforcing and the details within this reinforcing is what we call here design. For any one of these members, you need to be sure that you have enough strength, and this strength is greater than the demand. Sometimes we call the demand as the design loads. And the capacity we call the strength. So strength is equivalent to capacity, demand is equivalent to design loads. So if someone say here, let's say design moment, what does it mean by design moment? Design moment is not the moment capacity, it's not the strength of the beam. It is going to be the demand or the amount of moment that you want your beam to support. So we don't want to be confused between the terms. So let's say that you have here a concrete slab, and this concrete slab supported on 2 beams. How do you design the slab? You say the slab, I'm going to be just taking here a strip of the slab. And this strip is going to be representative to the entire slab section. Because what is the difference between this strip and between another strip that's right next to it? Let's say right here, right here. They're going to be all the same. When you look at it, they have the same loading, they have the same span. So where is the slab span? So the slab span, I'm going to say this beam support the slab. And this beam also is going to be the other support of the slab. So if you like to draw it as a beam and 2 supports, so I'm going to say, okay, here is a beam that I'm drawing here, and here are the 2 supports. Here's one support, here's the other support. Now, where is this beam? You can say, here's a beam. Where's support? You can say, here is one support, and here is the second support. So in structure analysis, we draw the beam like this. We put a couple of supports, like the way we know it. But in reality, it's going to be a slab supported with a couple of beams. Now, let's say I'm done with the slab design. Now, I'd like to design the beam itself. I'm going to say, where's the beam? The beam is going to be very similar to that. It's going to be also a beam with a couple of supports. Here's the beam, the first beam. The beam is going to be called from D to E. This is going to be like the support. So the beam is supported by columns, meaning that the support here is going to be one of these. This one is going to be one support to the beam. Here's the other support to the beam. Same thing for the other beam here. You have the support at G and F. And this support is going to be the column. So again, the slab is supported by beams. It spans between beams. Now the beam itself is supported by columns and the span between columns. So in our design, first we design the slab. After we are done with the section and the reinforcing, we move to the beams. We start to design the beams. We know the span, we know the loading, and then we figure out the design for it, section and reinforcing, and then after that we design the columns. So let's say that you have a point load which is called P here, which is right in the middle. As if you put here a point load on the top of this beam. If you like to go back to structure analysis. Here's the point B, P. This P would get moved to B and C, like two reactions. As if you have a point load here, and then you have two reactions. Now, when you look at this load, which is a reaction here, which is going to be at point B, now you consider again another beam. And you put here this reaction, which is coming from here, right? Now, this is going to be like a reaction. Yeah, consider it to be an action on the beam itself. Now, what's going to happen? This point load coming from the slab is going to get transferred through the beam, and then they are going to have two reactions here. So the load get transferred to the column. Again, this is what I call here the load path. Any questions? Yeah, no? All right, now let's look here at the slab section. This slab section, if you see here, this rectangular shape is going to be kind of repeated throughout the entire slab. So I'm going to call this is here rectangular section. But when you look here at the beam at the edge, it looks like an L shape. So I can call this to be L-shaped beam. And this beam here is like a T section. It looks like a T. Why? Because you have the beam, the drop of the beam, and then you have the flange. Here, the slab is going to be from one side, so I'm going to call it here L section. Same thing here. Look at this. This is going to be T beam, and this is going to be an L beam. You say, okay, but here it says T beam. What is the reason of this? That you consider this to be a T beam. When it comes to analysis of reinforced concrete sections, in the analysis part, we have either rectangular section or a T section. So you see here, I have your rectangular section. They have T section. We come to analysis. These T sections include T and L. The same principles and the same analysis that we do for T sections is going to be exactly the same thing that we do for L section. But when you go through the code, they just call it here T section. Whether you have the flange in one side or two sides, it doesn't matter. Now let's look here at the parameters of our section. If I have a rectangular section, total depth is going to be H. The depth to the tension rebars is going to be D, provided that I have positive moment. What does it mean by positive moment again? Anyone recalls? Yes? What is?
Positive moment is when it bends it upwards.
This
That's
is
how we
correct.
defined it.
When you have the tension at the bottom. So these three bars, we place them in the tension side. I want you to remember this. So D is going to be from the top compression to the tension reinforcing. H is going to be the total depth. This nomenclature, we're going to keep on using it to the end of the course. And this is going to be standard in concrete design. And the width is going to be B. This is going to be actually the width of the web. So in some codes or in some books, you're going to see it like BW, like what you see here. Web width. We are right next to it. Web width is B. This one here, D, we call effective depth. So what is effective depth? It's going to be D, not H. So what is H? Again, total depth. What is AS? This is going to be the cross-sectional area of the reinforcing bars. Oh. So it's going to be cross-sectional area of tension or tensile rebars. It's gonna be AS. Not just for one bar, for all the bars. When I have a section like this, I'm gonna be calling it here T section. And it's just gonna be the same definition, it's gonna be the total depth. And look at this, we take it from all the way on the top. We don't take it from here, right? We take it from all the way on top of the slab to the bottom fibers of the beam. BW is gonna be the same, the web width. AS, total cross-sectional area of the tension rebars. And you see here, sometimes we put them in one row, like in one layer. Sometimes we can put it in two layers. Now, the depth D is measured from the center of the rebar. Look at this. So the depth D here is measured from the centroid of the rebars to this, to the top of the beam. How about here, when I have two rows? When I have two rows, it's going to be right to the centroid of the rebar group. So it is not to the top, not to the bottom, it is going to be to the middle of them. Same thing, if I have this inverted T, right? I'm going to have D here to the tension rebars. Here's BW, and this is BF. What is BF? It's going to be the flange width. F stands for flange here. And this is going to be HF. What is HF? The thickness of the flange. Sometimes you call it also TS, just you know. What is TS stands for? Slab thickness. So it's the same as HF. Flange thickness or flange height, flange depth. So you can call it HF, you can call it TS, T sub S. This is going to be okay. If you notice here that the slab is extended in both sides of the beam. And the question is, what's going to be the effective width of the slab flange? Let's say that they have a beam like this. If I'm drawing it, just imagine that you have a beam like this. Here's the slab, one beam, another beam. I'm working on this beam design. How much width of the flange should I consider? So someone's gonna say you have a beam here and this is gonna be like free end. So maybe take this free end, consider it to be as part of your T section. And then here, take it half the way to the other beam. So you say, let me take it here from this beam to the mid span of the slab, like half the way, and this is gonna be your section. You say, yeah, let's say that this is okay for now, and let's see what the code says about this effective flange width. So this is now, you have an idea about the meaning of rectangular section and T section, and the symbols that we're going to be using for our variables. Here's one of our beams supported in two columns. It's going to be like a T section because actually in the reality, most beams are T sections because you're going to have a slab, right? And if you have a slab, it's going to be like a T section. You're not going to see a rectangular section like this in reality. It doesn't happen. But this could be a simplification for a beam case. Meaning, I may take this T beam, and if I want to simplify it, I'm going to say, here is my simplified beam. Just take this and do a rectangular section like this. Something like this. Does it make sense? It's kind of simplification, you know. So someone's going to say, you know what, this is going to be the same as this rectangular section in performance and on my design. But this is like ignoring the flange effect on the beam. So in reality, it is very rare when you see here an actual rectangular section, but it could be maybe a simplified case from a T section. So look at this beam here. It is exposed to vertical loads, and the vertical loads are acting downwards. And look what happened. At the bottom here, we have positive moment. Let's say this is going to be positive moment. And on the top, I'm going to have here tension on the top. I'm going to have negative moment. And here also I'm gonna have negative moment. What does mean by negative moment? Means tension is gonna be in the top, positive moment tension is gonna be in the bottom. Now this beam is gonna be supporting actual loads, meaning that we need to add some reinforcing. So in a case like this, I'd like to add some reinforcing here in the bottom. It's gonna be my main reinforcing to take the tension, and above the column, I'm gonna be adding some reinforcing. So the reinforcing here is to resist the tension. I'm gonna put it here in the tension side. So here the tension side is gonna be at the bottom of the beam because I have positive moment, and in the top of each column, I'm gonna have negative moment, meaning tension in the top, and this one I'm gonna place my main reinforcing bars. Okay, yeah, it makes sense. You put the rebars in the tension side. Let's look here at this section AA. Look here at this section AA. Compression is gonna be in the top. Usually when you have compression, you're gonna do here the neutral axis. So let's say here's your neutral axis, right? And then you start to do some hatching. This hatching means compression. So look here at this beam. Compression is gonna be in the bottom. Here, compression on the top. So this is another section AA because it depends on the amount of moment and reinforcing. So I'm gonna say maybe neutral axis is gonna be here, like in this case, or in here, right? And this is gonna be the compression zone, and the tension is gonna be in the rebars. Look here at section B, which is right above the column. Compression is gonna be in the bottom, and tension is gonna be in the top. And this is gonna be the reinforcing that I'd like to add here above the column, like in here, this case. Any questions? I'd like to hear from you guys. If I have any issues, we can catch it now. You're good?
I have a question, Professor.
Absolutely, go ahead, please.
I'm not sure if it's kind of a dumb question, but when you have a slab and you have the beam supporting it,
Yeah.
How are they connected? Are they like bolted, or is it like plastered? Or...
Cast it together. We pour the concrete all together.
Oh,
When you pour this, right? Let's go to another one like in here. You don't pour the beam first and then you pour the slab. You have the formwork, and the formwork is gonna be running like this. Right? And then you put all the reinforcing, and you put also some ties. The ties gonna be like this. I was gonna say, how does it look like? I'm gonna say, like in here, like this tie. And then you pour the concrete, and of course you have some reinforcing in the slab. So we are just simplifying it. We're not showing lots of rebars, right? Let's say you have rebars in the slab top and bottom, and you have the beam top and bottom, and then you cast the concrete all in one shot. So we call this monolithic. Monolithic means that they're going to be acting as one piece. Good question. Thank you. I'm looking here for the reinforcing details. So let's say here's a column, another column, and here's the beam. You need to understand that some reinforcing here in the column is not shown for clarity. The ties were not showing this closed or stirrup ties because it's going to be very complicated. It's going to be complex. It's going to be crowded. You're going to be showing lots of stuff that you don't really want to talk about. But look at this. I'm showing here the top and the bottom reinforcing of the beam. I'm going to say here the column and here's the column. Expected that I have a support and a support. This beam is kind of continuous, but this is going to be the first bay of the beam, the first span. I'm expecting positive moment to happen here. So here's going to be positive moment, which means at this side, I'm going to have tension. While right above the column, I'm going to have negative moment. It's going to be negative moment, and this is where I'm going to have the tension. Tension here is giving the top, tension is giving the bottom. These rebars, you cannot bring one piece of rebar and run it across the entire building. You need to start and stop the rebars. Just because how would people handle it, right? You have iron workers, they need to handle the rebar, take it, put it in place. This is gonna be like very frustrating if you try to take one piece of rebar and you want to install it in place. So in a case like this, you need to start and stop the rebar. So in reality, this rebar doesn't do this. In reality, you're going to have a bar like this. If I may take these two rebars, one bar is going to be like this, and the other bar is going to be like this. They're next to each other. And in reality, they are not on the top of each other. They're going to be next to each other. But if I show it next to each other, it's not going to make it clear because you're going to say, where is the first rebar ends? Where is the second rebar starts, right? It's not going to be clear to you. So just for the visual explanation, we're just doing it like this. Or also you can do it this way, but does mean that you're going to be bending the bar this way, right? We call this a splice. So the two rebars going to be next to each other. It's going to be like this, next to each other. We call this lap splice. What does it mean by lap? Lap is going to be this length over which we are putting the rebars together. A splice because you're splicing the bar. You have one rebar here is going to stop. This rebar is going to be continuation of it. If you notice here, when I wanted to put the splice, I put in the compression zone. I didn't put in the tension zone. Can you see this? Can you confirm it? Is it true? Yeah? Yeah, look at this. Tension the bottom, compression the top. This is where I put the splice in this section here. Tension the top, compression the bottom. I put the splice in compression, and this makes sense. Because when you have tension the rebar, it's going to be kind of tough to transfer the force from one rebar to the other rebar in tension without causing some cracking. So in a case like this, you'd like to put the splice to be in compression as much as you can. So okay, makes sense. Here is some slab rebars. See, you have tons of rebars here, right? And you're going to have a top and bottom in both directions. So actually the slab rebars that I'm not showing here, you see this? If I show here the top and bottom like in here, top and bottom rebars in both directions. So actually it's going to be complex. Look at this. You have rebars coming this way, rebars coming this way, and I'm not even showing any beams here. Look at the column reinforcing. Here's some columns. Here's the reinforcing. Some of these columns are casted already, and the rest of just waiting for the formwork. And here's the formwork, and then they're going to be casting from the top. Okay. Some round columns. We call this a spiral columns, usually for bridges and big buildings, parking structures, like covered halls, but not in the regular, let's say, office building. I mean, there is no need to do this. And as you see here, the support or they carry the cage, the steel cage, the reinforcing. They carry it with a crane, put it in place, put the formwork around it, and then cast the concrete from the top. Here's the footing. So someone's gonna say, where's the formwork? Here, I see here's some formwork. I understand, here's a form. And here's some form, right? And here's the form. You see this? This is the form here. This is plywood. So this here's some formwork. And they're going to be casting the concrete on the top of it. It's going to give you the shape of the concrete. But
Professor,
yes,
what were you saying? There's form work? I didn't understand that.
the formwork. Formwork means like form. You know, if you like to cast concrete, you need to have a form. So this thing here that you're looking at in this picture, you see it? This can be a form, like a mold, if you like. You're gonna put this in here, put the reinforcing bars inside, and then cast the concrete inside. So it's gonna be forming the concrete column for you.
It's like boxing the form, right?
Yeah, it's like boxing. This is correct, but we call it here formwork. This is a standard way of calling it. Like in here, look at this. Look at this. You have the form, which is this black thing around. You see this black sheets, and then you have some members, right, to provide the stiffness of the form. And after they pour the concrete and the concrete is hardened, they release this form. They took it out, and once they take it out, you're gonna end up with a column like this. Same thing with the concrete slab. They put first the formwork is gonna be flat. It's gonna be supported on some shoring. showing like steel members and sometimes aluminum members. And then they put the reinforcing on the top of the form. And then after that, they put the concrete from the top. And then they wait a few days, and after the concrete is hardened, they release the form. They take it out. Sometimes they say, they strip the form. When they take the form out, you're gonna have here clean surface of the concrete slab. If you look here at this footing, there is no formwork, right? We use the soil just to make it cheaper. We just dig a hole, and you see it's kind of irregular. It is not really straight. It is not like the formwork. It's not like this column. You see how the column is gonna become smooth and perfect. It's gonna be flat like this column here, or like this slab here is gonna come flat and perfect. And then we say, actually, to put a form here around the footing is gonna be a cost item, and you'd like to save it. So we're gonna say, you know what? Let's dig a hole which is gonna be slightly larger than the actual size of the footing that you wanted in your design. So let's say if the footing size 6 feet by 6 feet, meaning this dimension here 6 feet by 6 feet, and the depth is 2 feet, and I don't want to spend any money on the formwork. So instead of having it to be 2 feet, I'm gonna make it, let's say, 2 feet and 6 inches. Instead of having it to be 6 feet, I'm gonna make it, let's say, 6 feet and 3/4 inches. I'm gonna be adding a few inches right and left. So I'm gonna give you here a little bit larger concrete footing, because I know that the soil side is not really straight, right? It's gonna be expensive to spend the time and make it straight. And then don't forget, at the end, the whole thing here is gonna be covered. But here, this column is gonna be exposed, and this column here exposed. This slab is gonna be exposed from the bottom. People's gonna see it, so we care about it, or we care about the shape of it. But in here, in a footing like this, we don't really care. Then we just do it in that way, right? And just cast the concrete inside. Look at the reinforcing here, top and bottom, both directions. This side and this side. Then look at the 3 bars sticking up. The 3 bars, actually, this is what we call column dowels. This is gonna be the reinforcing going to the column, because the column is gonna come on the top of this footing. I have some retaining walls here. This is what you call a retaining wall, and definition of a retaining wall is gonna be a concrete wall or a masonry wall that supports some soil behind it. So you have here some soil. This is what we call here retaining, because it retains the soil behind it. When it comes to any design, like what I said before, when it comes to any concrete design, or even structural steel design, or wood design, or aluminum design, if you're doing a structural design, you may have an axial load, or a moment, or a shear, or a torque. Axial load, usually we use the symbol P for axial load. For moment, we use M. Shear, we use V. For torque, we use T. Yeah, we know that. I'm sure that maybe you guys have seen this already. When I say here VPN, it means the capacity or the strength. When we say here P sub U, it's going to be the demand or the strength needed. This is going to be the design. So what is this? Design axial load. What is this? Axial load is strength or capacity. How about this Vman? What's the meaning of Vman? You can say moment capacity or moment strength. How about this M sub U? Moment demand or design moment. So I'm going to take the moment as one example and write this next to it. So I'm going to say this is going to be design moment, or I'm going to call it here moment demand. Okay, I understand. So here it says moment. I guess you can apply it for shear. For shear, you can apply it for axial load. It's going to be your call. How about this side here of the equation? Vman, what is this Vman? You can say Vman is going to be moment strength. I can also call it flexural strength. I can also call it moment capacity. One of this, I mean, any one of them is going to be okay. So when you have any design, you need to have a strength or capacity higher than or equal to the demand. This makes sense. If the applied moment, let's say, is going to be 100 foot, you want the beam to be able to resist something higher than this. You need the strength, let's say, to be maybe 102, 103, 105, 110, any number higher than 100, because 100 is what you wanted to support. Within this terms here, I'd like to understand, why do we say phi, what is N, what is U? I understand when it comes to axial load, I call it P. I use the symbol here, P. Moment, I say M. Shear, I say V. So, okay, so how about phi? What is this phi thing? You can say this phi is a strength reduction factor. This is where I'm going to have some safety. So safety is going to go into the strength reduction, which means you're going to be taking some nominal strength. Look at this, nominal strength, reduce it by multiplying it by phi, because I say here phi Pn, right? Phi Mn, phi Vn. So again, I'm going to be taking here the nominal strength for axial load, or flexure, which means moment, or shear multiplied by phi factor, which means I'm going to be reducing the strength. The strength is the same as the capacity, right? So understand the term N here, N stands for nominal, P is going to be for axial load, P is going to be reduction. This reduction factor ranges, let's say, between 0.65, let's say, to 0.9, depends on what you're designing. We're going to be going through this in detail. But you need to know that the phi factor is going to be less than 1, right? This is strength, it is a reduction factor. It's going to be less than 1.0. It cannot be more than 1, right? Because you are reducing the capacity or the strength. Now, the ultimate demand. What is the ultimate force? Ultimate axial load, ultimate moment, ultimate shear, which is the demand. We call this the ultimate. So ultimate is not the strength. Ultimate is the demand. Now, we have few types of loads, right? We have something that we call here dead load and life load. Are you guys aware of the term dead load and life load? See here, lots of people will say yes. Very good. Dead load is going to be the self weight or the steady weight. Let's say that I have furniture, I have people. This is what we call here life load. You say, how about a permanent equipment like an AC unit in the rooftop? Is this life load or dead load? Edwin, are you there? Edwin, you have an answer?
Yes.
Weight of an AC rooftop unit. Is it dead load or life load in your estimate?
Dead load?
It is permanent. Right, this is correct, Edwin. Thank you. It is a dead load. Why? Because it is permanent load. It's going to be there forever. Life load is going to be the loads that you may change. Furniture, I can move the furniture easily. I know some people would say, but furniture, I mean, look at this table here. I didn't move it for years, but I still call it life load. So the problem is when you have dead load and life load, and both of them is going to give you, let's say, moment, or it's going to give you axial load on a column or shear or whatever, right? Can I just add it to each other? I mean, can I just take the dead load and life load? So I understand dead load. Dead load is going to be the self weight of the items, the self weight of the structure itself, of the concrete. And self weight, let's say I have concrete slab, I'm going to have floor system that I'm going to put there. Let's say like tiles, if you like to call tiles, it's going to be a flooring system. I'm going to have some pipes hung from the underside of the slab. I'm going to have ducts, mechanical ducts. I'm going to have light fixtures, and everything is hung here from the bottom of the slab. I'm going to call all of this to be dead load. Can you figure out the exact weight of all of that? You know, say, well, for the concrete slab, yes. But let's say that I have 10-inch thick slab, and during construction, they cast it to be 10.5. Can this happen? Yes or no? Is there any possibility that the slab thickness can be larger or thicker than what I designed for? Would it happen or no? Would never happen. Isaac? Would it happen?
I think it will.
Yeah, I mean, slab thickness is so easy. I mean, I'm sure that you have seen people working there on the site, and half an inch, no one's going to be catching it. So I'm not certain about the self weight of the members because it could be a little bit thicker. Also, I'm not sure about the weight of the tiles. When I do a design here, I'm going to put a value for it. I'm going to say, let's say 5 pounds per square foot. And all of a sudden, the person who's doing it, he decided to put porcelain tiles. It's going to be maybe 3/8 of an inch thick. He's going to put a little bit of a mortar. All of a sudden, the weight is larger than what I designed for. How about the mechanical ducts? Can you confirm exactly what mechanical ducts is going to be installed below the slab? I'm going to say no, not really. You'd never know what they're going to be installed. This is why I have some uncertainty about the dead load. All right, let's look here at the life load. How about life load? Can you figure out the exact weight of furniture that people would use in the house? You'd never know. I mean, I don't know. Or how many people is going to be there in this room at a time? I don't know. So also I have uncertainty in the life load. So what the code says here, this is going to be the CPC, California Building Code, in this section 1605. It says here, load resistance factor design or a strength design. So for us, it's going to be concrete, we call it strength design. If you are doing steel, we call it LRFD. So I'm going to say this is going to be strength design. I'm going to say here in the strength design, I have some uncertainties when it comes to the actual load that you're going to put there. This is the reason I'm going to have here load factors. So if you tell me here the dead load is going to be, let's say, 10 kips, I'm going to say, you know what? I'm not going to be using 10 kips. I'm going to add a little bit to it. I'm going to use here load factors. And how much increase are you talking about? I'm going to say when it comes only to dead load, it's going to be 1.4, which means 40% more in my design. You can call this safety if you want to, kind of a safety factor. But for us, we call it load factors. And look at this. It's going to be load factors. This is going to be like an equation number in the code, right? So what is D? D is going to be dead load. What is L? Life load. What is LR? It's going to be roof life load. Load pressure. This and you have a water tank. How about if I just have concrete slab or concrete beam? Do I have this F? No. So in many cases, I don't have lots of the symbols. I don't really have these forces. And in our course here, I'm going to be using dead load and life load only. So I'm going to say, this is what I have in our course. So any other loads, I don't really need them. Meaning, forget about this. Forget about this, right? I don't have this. I don't have F and T. I don't have H. H is going to be soil. When do you think I'm going to be using soil? When I have a retaining wall. In a retaining wall, it's going to be H. And here, I don't have snow, I don't have rain, right? I don't have any of that. So actually, when I do here strength design, I'm going to have here two equations that I want you to consider. The first one says here, consider 1.4 dead load. How about the second equation says 1.2 dead plus 1.6 life. Where do these two equations come from? I'm going to say it's coming from 16-1 and 16-2. Can you see them? 1.4 dead versus 1.2 dead plus 1.6 life. The rest of the equations, I don't really need them when it comes to dead load and life load. So I'm going to say, what are we doing here with these two equations? I'm going to say, this is simple. If you have some dead load and life load, you need to try both of these two equations and pick the one that controls your analysis, the higher of the two. Should you do a quick example? You say, okay, yeah, why not? You say here, I have a dead load of 10 kips. I have life load of 6 kips. What's going to be the design load? This is going to be like P dead load, P life load. I'm going to say PU equals to what? I'm going to try here both of these two options, both of these two equations. We call this load combinations. I'm going to try 1.4 times dead, 1.4 times 10, 140 kips. Okay. So 140 kips pays on the first equation. How about the second equation? I need your help. P sub U equals 1.2 times 10, which is a dead load, plus 1.6 times 6 kips. How much is the total now? Help.
21.6.
21?
Yes, 21.6. That's what I have here.
This should be 14, right?
Mhm.
Okay. Are you sure? 21.6?
Yes, so 1.2 times 10
Good.
plus 1.6 times 6.
So which load combination here controls? What's gonna be your design load?
What would ultimately be greater?
This is gonna be the 21.6 kips. So I'm gonna say which one controls. I'm gonna say 21.6 kips. This is gonna be my design load, and this controls. It's gonna be my design load. I'm gonna take the higher of the two. This is what we do with the load combinations. And it could be PU, it could be M sub U, it could be V sub U, it could be shear, it could be moment, right? This is why it says just dead. Dead doesn't mean just the load. It could be moment, it could be shear, it could be axial load. Does it make sense? All right, good. The strength reduction factor, what is that? We said that we're going to be taking the nominal strength multiplied by phi factor. Where is this at? I'm going to say right here. Strength, nominal strength multiplied by reduction factor. This one here is going to be the load multiplied by load factor. So the load factor is going to be more than 1. The reduction factor is going to be less than 1. Because when you have here demand and the strength, so you'd like to reduce the strength a little bit, and you'd like to increase the demand. Why do you increase the demand? Why do we have load factors? I'd like to hear from you guys, if someone can help me with this. Why do we have all of these load factors?
For a safety reason?
The reason of having load factors, what is behind that? What is the concept?
Uncertainties in terms of unknowns.
This is correct, like uncertainties in terms of dead load and life load. We're not certain it's going to be that much dead load. It could be higher. Same thing for life load. So we're going to be adding a little bit to it. So this one comes to demand. You'd like to increase the demand, right? To get like a good design. How about the strength? Why do we reduce the strength? Why do we have this phi factor, do you think? I mean, we have phi factor goes between 0.65 to 0.5. Why do we reduce the strength of concrete? You see, because labor, right? Quality of the product that you're going to be having at the end of the day. Expected material properties. Sometimes you design, let's say, for 5,000, but reality is not going to be really 5,000. And the rebar itself, it is true that we take specimens and we test them, and we show that the concrete strength is good, but you would never know if the specimen that you have taken of this material represents the actual material, correct? When you go here to concrete, let's say that you are pouring concrete, and then you take a cylinder and then you test it. You'd assume that this concrete cylinder represents all the concrete. But reality is, when you are taking the sample, they give you the best concrete in the truck. And the rest of the concrete in the truck, they're going to be adding more water to it. So the cylinder that you have taken is not really representing the concrete that you cast in this slab or this footing. So you got to be careful, right? In your design, you need to reduce the strength a little bit to account for all of these problems. This phi factor, as it says here in this table, we're going to see how to use it in this table. It's going to be coming later on. If this member is going to be tension controlled, it's going to be 0.9, compression controlled like columns and so forth, it's going to be either 0.65 or 0.75. If the spiral column, it's going to be 0.75, rectangular column is going to be 0.65. When you have shear, we're going to be taking 0.75. So you see this phi VN for the shear is going to be 0.75. For beams, it's going to be 0.9. For columns, it's going to be 0.65. It is not so clear what does mean by tension control, compression control, but later we'll figure this out. We know exactly what you're talking about. Difference between tension control and compression control. It depends on the amount of strain that you're going to have on the bottom of the beam. But we don't know yet how to figure out the strain. This is going to be a new topic for us, right? So we're going to say it depends on the amount of strain in the tension steel. You may have a phi factor of 0.9 or phi factor of 0.65. So what is this chart about? It is between on the x-axis, is going to be the tensile strain in the steel versus the phi factor. I cannot consider that this now here is covered. We're going to be going a lot in details about this. I'm going to show you how to use it. But first, we need to know how to do the strain analysis in concrete members. Questions before I move to the next slide set? All right. Now this slide set number 4. Now we're going to be working with rectangular concrete sections, reinforced. The same beam that you're talking about, and this is going to be the slab, and the same beam sections, right? Can have rectangular versus T. And I guess now we know where to put the tensile rebars. We're going to have here tension side, tension side. Now let's look here what happened to a beam. I'm going to start here with a rectangular beam. Reason because I'm sure this is going to be simpler than a T-beam, right? Look at this. Which one do you think is simpler? The T-beam with the flange effect or just like this? I'm going to say this is going to be the simplest beam section that I can work with ever. So I'm going to say, let me start with this. And then later, we're going to be moving to T sections. So in this beam here, at the beginning, concrete is still intact, no cracking yet, and concrete taking some tension. Now, all of a sudden, concrete is going to be cracking. Tension, and the rebar is going to be triggered. It's going to start here to carry some tension force. So compression side is going to be in the top. Let me see here, this is going to be compression. And this side is going to be tension. Understand that. And the neutral axis is going to be somewhere there. So I'm going to say, you know what? Here's the neutral axis. Just assume to be here. Concrete below this neutral axis is going to be in tension. It's going to be cracked, not working with us. It doesn't give any strength. But the rebars is giving me some strength because the rebar is going to be in tension. And above the neutral axis is going to be in compression. We're going to say, look at the strain here distribution. The strain here is going to be the maximum compression strain, and here is going to be the tensile strain in the steel. In the middle, actually, this line does not exist from the neutral axis to here because concrete below the neutral axis is cracked and it is not working with us anymore. Now let's look at the stress-strain relationship for the concrete and the steel. For concrete, strain is going to be on the x-axis, and stress is given the y-axis. This side is going to be the compression side, and this is going to be the tension side. I understand that concrete has a little bit of strength in the tension, but we're going to be ignoring this in our analysis, right? So in our design, we just ignore this. And how much is the stress here in this value? The strength? This is going to be FCR or FR, the cracking stress. So this is going to be in tension, and this here is going to be in compression. Concrete is very good in compression. What did we say about failing of concrete? Where do I assume that concrete is going to be failing? Anyone remembers the value? We said concrete is failing at strain of? Yes?
Isn't it 0.3?
0.003. Code says it is true that the concrete is going to be able to attain higher strains, but for us, we say once it reaches 0.03, we just say concrete's gone. Now, when it comes to steel here, tension compression is going to perform the same. as long as the rebar itself is going to be contained or braced, because the problem here, in tension, there is no buckling. The problem, once you start to apply here some compression on the bar, it's going to buckle. So as long as the rebar itself is contained in concrete and is prevented from buckling, you're going to have similar performance in compression and tension for the steel. We call this the yield point, F sub y. The slope of this line is 29,000 KSI, standard for all steels. This is going to be the model's plasticity E sub S. So, okay. How about the strain here distribution? I'm going to say we are studying here the capacity point. Remember what I'm saying here? This is study again for the capacity point. It's not about the cracking point. We're done with the cracking point. That was just a study. But now it's going to be for design purpose. So here at this distribution and stress and strain is going to be at the capacity point. At the capacity point, the concrete is going to be cracking, meaning this value here, the strain value, is going to be equal to 0.03. If the code had said 0.05, I'm going to be just going here with 0.05, right? But in our code, it says 0.03. So I'm going to stay here with 0.03. At this point, the section fails. Section didn't fail because of the steel. It fails because the concrete is crushed at 0.03 strain. It is not because of the strength of the concrete. It is going to be because of the strain of the concrete. And here's the neutral axis location. And I guess from these two triangles, from symmetry, I should be able to find out this epsilon S. You guys agree? This value here is going to be the same for all sections, all size of concrete members, all reinforcing bars. You play with all dimensions of the cross section of the member, right? And you play with the amount of reinforcing, but this value is not going to change. The capacity strain here is going to be 0.03. This is going to be at failure. The amount of steel strain can be determined from these two triangles. Don't you guys agree? I say, yeah. If you give me X and give me this, yeah. I can say the strain in the concrete divided by X equals to the strain in the steel divided by D minus X, which is the distance from here to there. So, okay. Here's the strain. How about the stress? Say, how would you draw the stress here distribution for the concrete? Yeah, say, this is simple. The strain here is equal to how much? Can someone help me with this? The strain at this point? 0. Good. Thank you, though. So the strain here is going to be 0. So the stress is going to be 0. We're still at this point here. Let's here change the amount of strain. I'm going to make it here 0.001, like 1/3, which means take here a vertical line at 0.01 and look how much is the stress and draw it here. So actually, this diagram that you're looking here at is going to be the same as this diagram, isn't it? With a little bit of tension. So this diagram actually, it looks like the stress distribution or the stress strain relationship. For each amount of strain, you have this corresponding stress based on this diagram. It's going to be the stress distribution. If you remember, we said the compression of the concrete here is going to be equal to this volume of the stress distribution over this rectangular section. Meaning I need someone to figure out the volume of this weird shape. So someone's going to say, this is going to be tough. How about the centroid? Where is this located at? Right? This compression force here. Where is centroid of this shape? I know when you have rectangular shape, it's going to be in the middle. Triangular distribution is going to be in the top 1/3, let's say, if this is going to be like triangular distribution. But for this, what should I do? I'm going to say nothing. Now, code says, ignore this tension in the concrete. I'm not going to be working with this piece. Just ignore it. Say, okay, I can live with that. How about the tension in the steel? I'm going to say tension in the steel. You can figure it out if you have the amount of the strain in the steel, and then go to this diagram. You say, I'm going to be in the tension side. How much is the strain in the steel after you calculate out here? This gives you like this value You just draw a vertical line, figure out the amount of stress, and just use it. The tension force equals to Fs times As. So I'm going to say here, compression is going to be the integration or the volume of this distribution. The tension force equals As, cross-section area of the steel, multiplied by Fs, the stress in the steel. If you find out the strain in the steel, it is going to be like here, right? It means the tension in the steel is going to be equal to Fy, which means the highest stress value that you can ever get in the rebar, multiplied by the cross-section area. So now it's going to be like Fy. For me, it is just Fs. It's the stress in the steel. Any questions? So it looks like it's going to be very similar to what we have in this cracked concrete. We have tension compression, and they're going to be equal to each other. But the problem that I'm facing here is going to be this shape that I don't like. This is why we're going to be using a simplified block distribution, which is this one here. We're going to be using a rectangular section because we cannot really work with this. Who's going to be doing this? It doesn't make any sense. So I'm going to be using here a simplified stress block. It's going to be called Whitney's stress block. I came here to a stopping point. Please sign out, type your name in the chat box, in the chat room. If you have any questions, hang around, please.